Today we want to talk about limits. We have been very hand wavy about talking about limits. So let's remind ourselves of what the idea is. So over here in this diagram, we can see a function. And in this function, as x is approaching c, as the values of x get closer to c, f of x gets closer to L. As x approaches c, f of x approaches L. What we are saying is that the limit as x approaches c of f of x equals L. We're saying the limit as x approaches c of f of x equals L. We mean as x approaches c, f of x is approaching L. That's just our intuition about what this statement means. We would write, our notation for this will be the limit as x approaches c of f of x is L. That's our notation for what is going on. We write the limit as x approaches c of f of x equals L. We mean as x is getting closer to c, f of x is getting closer to L. This is what we write. This is how we speak what we're writing. This is what we think about what we write. We need to define this because this is math class and we need to have workable, rigorous definitions for things. So we say the limit as x approaches c of f of x equals L if and only if and now we're going to write stuff down. The limit as x approaches c of f of x equals L if and only if for every epsilon greater than 0, for every positive epsilon, so if and only if, for every epsilon greater than 0, my habit of writing epsilon is to write a small backwards 3. There's a lowercase my lowercase epsilon. This is unfortunately later on, if I write it a little bit bigger, going to be my uppercase sigma because I can't be bothered to write angly things. But in this case, it's going to be epsilon. The limit as x approaches c of f of x equals L if and only if for every epsilon greater than 0, there's a delta greater than 0 such that this is how I'm going to write a lowercase delta. I'll write like D sans serif that's been backed into by a truck, causing a big old dent. The limit as x approaches c of f of x equals L if and only if for every epsilon greater than 0, there is delta greater than 0 such that the absolute value of x minus c less than delta implies the absolute value of f of x minus L is less than epsilon. Pause for copying. Oh, sorry, I shouldn't read that part of the teleprompter. Limit as x approaches c of f of x equals L if and only if for every epsilon greater than 0, there is a delta greater than 0 such that the absolute value of x minus c less than delta implies the absolute value of f of x minus L is less than epsilon. let's make some notation about the things that we are writing here. So, like I said, this little thing is epsilon. We think of this as our tolerance. This is the required tolerance. How close do you want f of x to be to L? The idea behind this definition is that we can make f of x as close to L as we want, so long as x is sufficiently close to C. Epsilon is how close we want f of x to be to L. I didn't leave myself space to write them. So epsilon is our desired tolerance. F of x needs to be within 1/100th of L. Delta is how close we need to make x to C, how close x needs to be to C to make f of x within epsilon of L. That's how we get within epsilon. So the lowercase delta is how close we make x to C to make f of x within epsilon of L. So delta is the thing that we go find. That if we can get a delta and say if we're this close to, if x is this close to C, then we're guaranteed to have f of x be within epsilon of L. So a delta is the one we're going to look for. It's a lowercase delta. That's how close x needs to be to C. So the lowercase delta is how close x needs to be to C. This is written with two absolute value inequalities. The absolute value inequalities say the difference between x and C is less than delta. So this absolute x minus C less than delta, this means that x is within delta units of C. That's how we could read this expression here. That absolute x minus C less than delta, we can read that as x is within delta units of C. If it's been a while since you've done absolute value inequalities, the way to undo the absolute value inequality is to say that x minus C is less than delta, but greater than negative delta. I spelled minus wrong. Minus is like one of the easiest things to spell in math. And I spelled it wrong. If we add C all the way through, we could see C is that base, and then we're either subtracting delta or adding delta. So X is less than C plus delta and greater than C minus delta. X is C plus or minus delta. Similarly, when we write absolute f of x minus L less than epsilon, we're saying that f of x is within epsilon of L. Solve our absolute value inequality the same way because it's set up in the same setup in the same way. Absolute value less than the number means that f of x minus L is less than epsilon, but greater than minus epsilon. That means f of x is less than L plus epsilon and greater than L minus epsilon. If we look at this, the picture, if we take this and send it over to the picture, when I say x is within delta units of C, x is between C plus delta and C minus delta, and we want f of x to be between L plus epsilon and L minus epsilon. So we're trying to make this happen. Where I have some L plus epsilon above and some L minus epsilon below. I'm trying to make f of x fall into this interval. And so we ask, how close do we have to put x to C to make that happen? So now all we have to do is to make sure that our delta is within these two values. So I make sure delta is inside this interval. Sitting there drawing this diagram, it's like, I'll make it a bigger diagram. You know you're going to be putting more stuff on it. It's fine. It wasn't fine. If I make x within delta units of C, we can see that we're guaranteed to get f of x to be within epsilon units of L. Usually we look at this, and the way I phrase this, I call epsilon is where you start, and then you go figure out what delta is. And then this raises the question, why don't you just use a smaller delta? You can use a smaller delta. We're not trying to find delta. We're not trying to find this. We're asking a different kind of question, a much more math kind of question. Can we make this happen? If the answer is yes, then we can say the limit as x approaches c of f of x equals L, because we can make this happen. I don't care about what the value of delta is. I just care that there's some value of delta. That makes sense? This is a very math question. This is our first very math question of the semester. This might be the very first math question that you've run across. It's like, well, is there an answer? Yeah. What is it? Don't care. This is not an engineering question. This is not a physics question. This is a math question. There's a conference that goes on, and an engineer and a chemist and a mathematician are all at this conference. They were all on the same flight, which was delayed several hours. They're very tired, and they all go to bed. Unfortunately, 4 hour, conference goers, they're all smokers, and they all fall asleep with a lit cigarette in the bed. All of their beds catch fire. The engineer smells the smoke and wakes up, runs into the bathroom, sees the sink and the ice bucket, fills the ice bucket with water, dumps it on the bed, and goes back to sleep. The chemist smells the smoke and wakes up, goes into the bathroom, sees the ice bucket and the sink, goes back, checks the composition of the mattress and the sheets, makes a few quick calculations, noting how fast the fire is spreading on the bed, goes back, fills the ice bucket up with a precise amount of water to put out the fire, including the amount of time it takes to get there and back, dumps the water out onto the bed, puts out the fire precisely, and goes back to sleep. The mathematician smells the smoke and runs into the bathroom, sees the sink and the ice bucket, recognizes that a solution to the problem exists, and goes back to bed. That's math questions. That's what we're going for here. I don't care what delta is. I just care that there is a delta. Does everybody see the distinction? The question isn't, what is it? The question is, can we do it? Because the way we want to think about this, the way that we have this set up, like I was there, the way that we set this up is that we can make f of x as close to L as we like, that's the epsilon, so long as x is sufficiently close to c. We can make f of x we can get f of x as close to L as we want, so long as x is sufficiently close to c. Not what is the delta, but is there a delta? It's not about what is the delta. The question is, for a given epsilon, is there a delta? Is there a delta for every epsilon? Want to make sure that we distinguish the questions. Is there, if, I spelled is wrong. Is there a delta for every epsilon? The question is not, what is the delta for some given epsilon? So in this case, it seems kind of obvious because I picked something where the limit as x approaches c of f of x is equal to L, and I drew a picture that fits that description. Let's see some pictures that don't fit this description. Let's say this line is at 4. This is at 5. And this is at 6. And here's our function. In this case, the limit, we would say that the limit as x approaches 3 of f of x does not exist. F of x is not approaching a value. So in this case, limit as x approaches 3 of f of x does not exist. F of x is not approaching some value L. F of x is not getting closer to any one value as x is getting closer to c. If we're coming at 3 from the negative side, from the left, from less than 3, it looks like the function is headed towards 4. But on the other side of 3, the function is headed towards 6. So we are not headed towards one value. This is where our default human thinking really messes with us, because we always just want to find an average. And so I put the value of the function at 5. Can we say that f of x is approaching 5? I mean, clearly the answer is no, right? So why can we not say that f of x is approaching 5? So we'll appeal to our definition. We can make f of x as close to L as we want, so long as x is sufficiently close to 3. I can't make f of x within 0.5 units of 5. So 5 is not a candidate for a limit. If I draw my plus and minus epsilon around the 5, there is no value of x that will put the value of the function in that little orange square. We'll never be close to 5. We'll only be close to 4 on one side and 6 on the other. I can make f of x within 1.5 units of 5, but that's not the question. The question says for every epsilon, not just for some epsilon. That make sense? For every epsilon, not just for some epsilon. So even though epsilon equals 1.5, it's like, well, hey, it works for me. The definition of a limit says it's not about you, 1.5. Think about someone else for a change. You selfish bastard. We also can't get within epsilon of 6. It works on one side if x is a little bit bigger than 3. But if I'm at 0.5 units of 6, if I take the limit, try to make the limit 6, if x is a little bit less than 3, then I'm getting 4. So it's not approaching 6. I can't use any of these numbers as a limit because we're never approaching one value. Note that the function is defined at 3. This doesn't matter. The function is defined at 3. F of 3 is equal to 5. We have a value for the function, but we don't have a limit. We're not approaching something. Any questions? We could say that the one-sided limits exist. We could say the limit as x approaches 3 from the left is equal to 4, and the limit as x approaches 3 from the right is equal to 6. But the limit itself, it just doesn't exist. We're not approaching some value. I made my x-axis way too wide for this example that I'm going to do next. Oops. I wasn't even showing you the example. Here we're interested in what's going on at 0. Here's another instance where the limit does not exist. The limit as x approaches 0 does not exist. As x is getting closer to 0 from the negative side or from the positive side, as x is getting closer to 0, the function is not approaching any value. It's going towards infinity. Well, in this case, the limit as x approaches 0 of 1 over x squared does not exist. Infinity is not a number. We can't use it as L. It's not a number. One over x is not approaching some value. It's off towards infinity. We can't express this idea that from both sides, this function is headed off to infinity. We might say the limit as x approaches 0 of 1 over x squared is approaching infinity. On both sides, the value of 1 over x squared is just going off towards infinity. But notice I did not say equals infinity. We don't get to say equals infinity. Equals is for numbers. Infinity shows up at the equals club, and the bouncer says, you're not on the list. Also, just wouldn't make any sense to say within epsilon of infinity. Don't think of infinity as a number. So the limit as x goes to 0, 1 over x squared approaches infinity. That means limit as x approaches 0 of 1 over x squared does not exist. The limit does not exist. What we want to be able to do as calculus people is understand what the definition, understand how to say the definition of the limit. Limit as x approaches c of f of x equals L if and only if for every epsilon greater than 0, there is a delta greater than 0, such that the absolute value of x minus c is less than delta implies the absolute value of f of x minus L is less than epsilon. We should be able to state that, write it down. We also need to understand what it means. We can get f of x as close to L as we want, that's the epsilon, so long as x is sufficiently close to c, that's the delta. We want to understand that this is an existence question, not a problem, not an equation to solve. For a given epsilon, is there a delta? Not what is that delta, is there a delta? And we just need to look at a bunch of examples where limits don't exist. We're going to do that in more detail when we talk about continuity. Any questions? Comments? Snide remarks? I have 2 problems for you to do before we adjourn for the day. They're of the type that we have been looking at. Find the equation of a line tangent to a curve at a given point. I'm doing this because we have derivative shortcuts as one of the tools in our tool. These problems we're going to work on for the next 10 minutes. And then we will be putting them in the class. We can help each other on these problems. You can look stuff up if you want to look stuff up. I know my limit of counting is 6, and that I can't count to 5 either. Can't count to 5. But I know when I get to a row and I get stuck on the counting, I should just pull 7.